So surprise, we have to take a test a day earlier, and I didn't have a chance to explain everything I wanted to explain yet. So here we are with a couple of problem types that we'll talk about on Thursday, but you might want to hear the explanation again. So here they are. Quickly, we're going to look at a two-way table and a marginal, not a marginal probability, but the idea of a conditional probability from a table. So the probability of survival given first class, that means we're going to go ahead and look in the first class column. That is a row, by the way. The probability that they survived was 197 people out of the 319 first-class passengers. So that's how, when you're talking about a conditional, you look at the given, find that section, and that's where your total is going to come from. Same thing again. This is the opposite idea, looking at third class. What is the probability that it's a third-class passenger given it's a survivor? So we're going to go ahead and look at the survivor column. This one's a column. And we're going to look at the third class. And the probability is 151 third-class passengers out of the 442 that survived on the Titanic. Now, one of the key issues you're going to have to do is to prove that two events are independent. And the way we prove that independence has to do with looking at the probability of the thing by itself has to be the same thing as the thing with the given. So we're going to look at that in the next. So if two items are independent, mathematically that means that the probability of a third class given a survivor is exactly the same as the probability of just being in the third class. So the third class is just the simple marginal probability of 627 divided by 1207, which is 52%. So 52% of the passengers were third class, but only 34% of the survivors were in the third class. So 30% of the probability that you were in the third class given a survivor is 34. So this shows that these two events, third class and survivor, are not independent because their probabilities are not the same. So the definition of independence is that the two events, the probability of A given B is the same thing as the probability of just A by itself. And if those are not the same numbers, then they're not considered independent. So that's something you kind of need to memorize. And if you're not given a two-way table or a Venn diagram to look at the overlaps, then you're going to have to, and they tell you that the two events are independent, then you have to go ahead and follow this formula. The formula says if I'm trying to find the probability of A or B, I'm going to take the probability of A, add it to the probability of B, and then take away that overlap. We know that. However, to find that overlap, you have to go ahead and just multiply A times B. So in this case, just a simple example, if the probability of A happening is 20%, the probability of B happening is 60%. If we want the probability of A or B, we would just simply take 0.2, add it to 0.6, and subtract 0.2 times 0.6. And that 0.2 times 0.6 is A intersection B. It's that overlap in a Venn diagram. It's that overlap in a two-way table, but in this case we're assuming that the two are independent, and we just want to have the actual data to pull that from. So this would be 8/10 minus 12/100, and I think that's 0.68, but I'm not really sure. Check my math. Anyway. So the general multiplication rule says that when we have independent events, and let's, for just argument's sake right now, let's assume that the weather is independent, each day is independent of the one before it. If you have the probability that it's going to rain, and let's assume that the Weather Channel says it's going to be a 25% chance of rain for the next 5 days, and the probability it's not going to rain is 0.75 or 75%. Those are considered complements, by the way. It's either raining or not raining. If we want the probability that it's going to rain in both days, the first day and then the next day, or assuming these are independent, then we're going to multiply them. 0.25 times 0.25. And that would be the probability that it rains on both of those days. The next example, and so let's say we wanted to know what's the probability that it's going to rain on all 5 days. We would go ahead and take that probability of the rain, and we would carry it to the 5th power, so 0.25 to the 5th power. So raining 2 days in a row would be 0.25 to the 2nd power, 6.25%. Raining 5 days in a row, you would take that probability and carry it to the 5th power. You're going to multiply it by itself. Once again, this assumes that these events are independent, and I'm sure rain and not rain are not independent of each other, but let's, for the sake of argument, say that. Now we're going to get into a tricky kind of problem that I need you to think about. This isn't saying that it's going to rain all 5 days. The next kind of problem is asking you to say at least one of the days. Kind of. And the last thing, this is a gnarly, confusing thing in my opinion. You're going to have to use your complements. So there are some problems where we're looking at the general multiplication rule, and the general multiplication rule says is if we want to know two independent things, so 9.6% of the people in the U.S. have these 10 most common names: Smith, Johnson, Williams, Brown, Jones, Miller, Davis, Garcia, Rodriguez, and Wilson. So if you chose 10 people at random, what's the probability that at least one of them has the names above? So you can't just take the probability of 9.6, change it to a decimal, and carry it to the 10th power, because that is asking what's the probability of all 10 of those people having one of those names. And that's not what the question is. So you want at least one of them to have the names above. So the first thing we want to find out is the probability that one person doesn't. That's the first thing we're going to find out. And so that's our complement here. 1 minus the probability that someone does, and that's 0.904. Then we're going to look at the probability of that the 10 people don't. So that's 0.904 to the 10th power. So nobody does to the 10th power. And that works out to be this number right here, 0.364. And then we have to look at that complement again. So 1 minus 0.364 is going to be the probability that one of them is. And so that's 64% of the chance that if you pick 10 random people, not necessarily from California, but 10 random people from the United States, you're going to have a 64 chance that they're going to have one of those names. Pretty wild. But the idea there is that first you have to think about you're not multiplying that original thing by 10 to the 10th power, please excuse me, because that is telling you the probability that all 10 of them have it. Instead, if you're only looking at least one of them, you have to go to the opposite of it, carry that to the 10th power, and then go back and find the complement again. It's tricky. I agree. That's why I'm explaining it right now, and I'm explaining it again tomorrow. Bye.